here. So I just wanted to establish the correlation analysis. When we get our data, we usually start with correlation. The correlation analysis, we plot the data just like we did sketch. And we kind of can see visually if we have a linear relationship. And it needs to be linear in order for this to work. Okay, so if it's not linear, you'll still get a value, but it won't make any sense. You'll still get an R squared, but correlation does not measure nonlinear relationships. Just remember that. That's one of the facts for correlation. Correlation R, if you remember, is a number between -1 and +1, right? The interpretation, so +1 denotes a perfect correlation, positive linear correlation, relationship. Perfect positive linear relationship. 0 means there's no correlation, so there's no linear relationship present between the two variables. -1 would be a perfect negative linear relationship. Negative. Okay. Let's just look at some of these just to remind you how that looks. We have R equals -1. You can see they're all lying perfect on a perfect straight line. They can be spaced out differently, but so long as they're on the same slope, it's going to be +1. Notice here there is some variation. So we have, that's why it's called a scatter plot. There's more scatter in the plot to the right. They're not lying on a perfect straight line. So we know then that R would be somewhere between 0 and 1, just because of visual inspection, right? You can see that it would be positive. What you do is you look at these and you imagine where the line would be, okay? So you want to follow the trend, look for the trend pattern. This one here, the plot on the left would be -1. They're all lying on a perfect straight line, negative line. But you can see in the right, plot in the right, there's a lot more scatter. So, but still negative. You can still see the trend is still, so it would be -1 to 0, right? At 0, it's just going to be straight across. So like R is 0 would be like this. Because for any value of X, you get Y. It usually is Y equals some constant, A. So that means there's no relationship between X and Y. X is not even involved, right? Because it works for any X. So that would be correlation 0. So here we have also, we can describe it as being strong or weak. The plot on the left would be strong. If it's 0.843, that's close. So the closer the value is to 1, then the stronger the correlation. Here, the plot on the right is more scattered. And it turns out when you calculate it, it is 0.189. So it's weaker, right? Right? It even starts, as it gets weak like that, it starts to get difficult to see if it's negative or positive. That's when getting the numbers actually help. Get that number. You can see it's still positive, but it's very, very weak relationship. And then here, negative, strong, -0.9. So again, values close to -1 will be stronger than values close to 0, like the one on the right, -0.368. So why am I fitting all this into regression? You can guess when you have a strong correlation, you're probably going to have a good model. For example, X and Y, if I was to build a regression model for the plot on the left, it's going to have a better fit, right? Than a model with the values on the right, X and Y, right? There's more variability on the one on the right, so the predictions would have larger error. And you can even visualize that with the line. So if you think of the error as being y subtract y hat, that's the error, right? For each one, the error would be the sum of all those. So remember the sum, the SSE is the sum of all those squares. So if you look at all of these, the sum not squared is going to be 0. So you can see that the error is smaller than if I did over here. Just need to bring it down. You can see that error, that is going to be much larger error than the ones on the left. This one would be larger than this one, right? So the error is the vertical distances from the y point to the line. So y minus y hat. So it's the y from the data. The first y is the y from the data, the raw data, and the hat is the y that you get from the line. So those vertical distances, you just find those vertical distances. So you can see that the model, the regression would be a much better fit. You'd have really good, trustworthy predictions with the model on the left. That's why it's good to get the R value. And you can see that if you were to square R, same thing, it's gonna be close to 100% on the left, not so much with the data on the right. So the data, right? You guys seen that? Yeah. So that's how correlation fits in. It's very important. We always want to know what the correlation is. We want to incorporate that in our analysis for regression. Okay. Right. Still showing negative. So correlation makes no distinction. If I was to swap the X and Y values, it would still come out the same number. So let's say I went, no, oh no, I've plotted this wrong. The Y should be X and the X should be Y. I would still get those values for R, right? Just the way the formula works. So you can swap them. So that's the first property. Second one is correlation is unitless. And it does not change. So if you go from, let's say you're using heights in centimeters and you go, no, I want inches, and you change the units, you will still get the same correlation. Because there's no units to it. You'll still get the same number. So you can change units. Correlation R does not describe curved. So it has to be linear. We talked about that. Must be linear. If you plot the data and you see some quartic, or if you plot the data and you see something happening like this, you're not going to run a linear regression on it. You can do a polynomial regression, but you can't even do a correlation analysis using these tools because Pearson correlation coefficient is only for linear relationships. That's why it's always important to just do a quick sketch or to get a plot of the X, Y variables to make sure. Because the numbers, the software doesn't know, and even when you're crunching the numbers, it doesn't know that if it's linear or not. You have to actually you actually have to plot it to see. Okay. Correlation R is not a resistant measure. So if there's outliers, you have extreme, even just one extreme value can change the entire value. So it is strongly affected by even one outlier. And then the whole regression line is also affected. So you have to watch out for those extreme values. So if you take a look at these two plots, the plot on the left, we have some data. And we calculate the correlation as being moderate, 0.342. So not close to 1, not really close to 0. So just moderate. Maybe even on the weak, if you had to pick between strong and weak, you'd say weak. This here is the exact same data right here is all this. It's exactly the same. I've just zoomed out and I've added 1 point. So I had to zoom out to get that point in. You can even look at the scale. The scale of the X only goes to 30. Here it goes to 40. So I've added an outlier. And then I've gone, okay, what does that outlier do to the correlation? And you can see it changes it to 0.753. So be careful. 1 point can make it seem like there's a stronger, like if you didn't plot this, or if you didn't look for outliers in your data, you would maybe just look at the numbers and assume you have a really great R because it's 0.753. That's a strong association. Meanwhile, you have this gap that you don't know about. So you have to really investigate. Another reason to plot the data, right? So yeah, definitely look at your summaries too to see if you're, you can look at box plots and you can look at each X and Y on its own. Yeah, so that takes us to R squared. We usually just call this R squared. I haven't been to too many meetings where we say, what's the coefficient of determination? We don't usually say that. We just say, what's the R squared on the model? So R squared, because R is a value between -1 and +1, then R squared has to be a value between 0 and +1, right? If you take a number and square it, it has to come out to between 0 and +1. So it's formally what we call it. It's the proportion of variability of the dependent variable y accounted for or explained by the regression variable x. Right. So we have all these sums of squares, and we have the variability. Remember from ANOVA, you have the two different sources of variability. This is one of those sources. Okay. So we call it the proportion of variability of y accounted for, explained by the regression line, right? By the independent variable x. So an R squared of 1 means you have perfect prediction. Quite often we'll express it as a percent. Usually we do it as a percent. You won't see 100% in real data. It won't happen. That would mean like it's just perfect. It just means perfect prediction y by x. So, but it's good to know where the bound is. So the closer R squared is to 100%, then the better the model fit. Okay, because this is one way to assess the model fit. And so the closer to 100% is good. Even a 60 though, we'll take. That's considered pretty good with real empirical data. It's not a bad number at all. We actually hope for those. A simple coefficient of determination is the square of the coefficient correlation that we know. And we calculated those with our example, right? Just to show you, let's go back up. We did that right here. We calculated R, and then we calculated R to be 0.977, and then we calculated squared, which was 0.955, which is 95.5%. Incredible. But again, based on 5. The larger data set, those numbers decrease, but it's a good way to see the association, right? And we're going to keep working with this example to get more metrics out of the regression to assess the fit, okay? We'll keep looking at these. So just bear with me. We're going to keep looking back at slide 9, okay? We need those sums of squares. So we're right back here. So the model assumptions is you have to assume linearity. The model is linear. The error terms have constant variance. We're going to look at that more with pictures in just a moment. We do model diagnostics using residual. We do a correlation analysis. We build the model, then we do a residual analysis. And we will do a residual is the same as error. The residuals, which is the same as the error. Residuals, errors. So I use those two terms interchangeably, errors, residuals. Residual just means the vertical distance between y and y hat. Same thing as the error term. They are also to be assumed to be independent and normally distributed. They need to look like that. So if your data, if your response variable, so the y, if you just look at your y response variable, what was our y again? It was sales, right? Sales. So if I was just to make a histogram of sales, if it doesn't look single peaked like a normal distribution, then what we do is we would do what is called a transformation. We will take usually the log of y. And so if you have data that looks like this, right, your y, and it's skewed to the right, and quite often sales does look like that. You might have a lot of sales grouped together, and then you might have some larger amounts out in the tails, and it doesn't usually look normal. So we just do a transformation. We take the log of y, and quite often it's so nice when this happens. You plot it and it comes out normally distributed. You just have to be careful though, because then when you make predictions using your regression line, you need to remember to back transform that. Right? You have to remember that if your prediction is log y, let's say it comes out as being 0.2, then you have to take e to the 0.2 to untransform it back into dollars. Okay. So we'll have more examples like that as probably after the midterm when we work on our project, because pretty sure the response is going to need a transformation for your project. Okay. But we'll work through a couple of examples at least to see that. So the standard error of the estimate, standard deviation of error. So we call it the standard error of the model, like of the overall model. We call it of the estimate being the model, the regression equation, right? And it tells us, so you can use that empirical rule. You can go, well, plus or minus 1 times the, so let's say your standard error comes out to be 2.1. Then you can say 2.1 plus or minus 2.1. The errors, right, are 68%. 95% would be 0 plus or minus 2 times the standard error. Right, so it would mean that is how much data falls in those ranges. Okay, remember that the empirical rule, what was it, the 68, 95, 99.7 rule, right? Again, it's assuming normality, right? You can only use this when you have normal data, which is why we do that transformation. Quite often we do it. Now, if you plot the y, you plot your response and it looks normal, then you don't need a transformation. You just leave it and keep on going. And we assume with our example that, well, we only have 5 points, so you wouldn't get much of a histogram out of 5 points. So we just assume that it doesn't need a transformation. Right, so we use this information, the standard error of the model, just to make a judgment about the fit, right? If it's the higher the standard error, then there's more variability and less precision. The smaller the standard error of the model, then more precise it is. Less error is good, right? You want a small standard error. So we don't just look at R squared, we also look at this value too, the standard error of the model. So let's see, there it is there. Okay, just gonna say, where's the formula? There it is there. So you want to get that SSE that we talked about. And you can choose which one you want. Now, we don't have, well, we do have the raw data. We could go through that. That would be too much time. And then you go, well, we know R squared. What, and we know SSYY, what we could use this one to get it, to get that SSE, or we could use this one. So why don't we use the one in the middle? So we'll do this as an aside. And we're gonna go 1 minus R squared. So that's gonna be, now we need to go back up to 9, right? At least to 9, let's see. So we want to get 1265.2. And our R squared came out as 0.955, right? Now you may do this a few different ways. Like you could try it with the other one and it will yeah, I mean, I could have put 0.977 in there and squared it too. So what do we get when we get that? Let's see what we get. So let's have our calculators. We're going to do lots of calculations. So 1265.2. Okay. Now, if we use the sums of squares, we might have got a slightly different number, but it's going to be roughly, I get roughly 56, 57, something like that. So going to be in that ballpark. So 56.934, but we're not done yet. That's not the standard error of the model. That's just the SSE. That's just the sum of the squares of those residuals, right? This is the sum of the squares of residuals. So we need to keep going here. Let's do 56.934 divide by, what's our N? How many points did we have in our raw data?
5, right?
5, yeah. 5 minus 2. So that will give us 3 in the denominator. So we just make sure that all stays in your divide by 3. And 3 will be the degrees of freedom for this model. And I get 4.36. 4.36, something like that. So it should be close to that. And so what that means is you can say 0 plus or minus 2 times 4.36 will have 95% of the data. The errors will be within 95% of that. And that comes to 8.72. Plus or minus, right? It'll be plus equals plus or 0 plus or minus that. So it will be negative 8.72 to positive 8.72. That's negative 8.72 to positive 8.72. That's 95% of the errors will lie in that range. 95% of the errors. Hey. Yeah, we're still doing the online chat feature example. We'll keep going with that. And we're going to keep assessing the fit of the model by, we can test. You're going, oh no, hypothesis test. Actually, kind of neat the way we do it with regression though. So it's always, with the software, we're always testing whether the slope is equal to 0 versus not. And if you think about this in just context, if the slope is equal to 0, right? Let's get our equation. What was it? Oh, that's hard to see. What was our equation? Y hat equals 75.222 plus 0.519 x. Is that what we have? Someone check that for me. I believe that was our equation for our online chat feature. Correct? Yeah, all right, we get confirmation there. So imagine if the slope coefficient was not 0.519, if it was 0, what would that mean? Would we even have a regression? We would just have an intercept, right? Like if the slope coefficient is 0, this is the slope coefficient right here. That's the slope, 0.519. If it was 0, you wouldn't want this model. You wouldn't even use it, right? If 0 was a potential possibility. So we usually do the first case. You can go greater than or less than, but we usually do a two-sided test. The software default is always two-sided. If you did this in Excel, you would get a two-sided hypothesis test. And we always want to test the slope. We don't ever care about the intercept. We don't ever test the intercept because it's just where, you know, when x is 0, where would y cross the y-axis?
So having the slope as 0, what does that mean for the analysis?
So this is why we do this part. It's a good question because if the slope is 0, if we test the potential of it being 0, and you can see that it's 0.519, but we know that we can build a confidence interval for that. And if the confidence, it goes right back to the first lecture. If the confidence interval contains 0, then I don't want this model because that means the slope could be 0. And if the slope could be 0, then all I have left is an intercept. I can't make any predictions. I wouldn't really trust the model. So what it says also, if the confidence interval was 0, or we test it in a hypothesis test and it comes out, we can't reject it, it could be 0, then we can even jump and make the conclusion that the online sales and the time spent on the chat feature are not significantly related because of that, just by testing the slope coefficient. So you can see now the power of these hypothesis tests and confidence intervals in this context. So much, it's just so much easier to see too, right? We're not just dealing with it. You go, well, geez, if the slope was 0, I don't want a regression line where the slope could be 0, right? Like it's a potential value. So we do have a slope of 0.519, but we want to test to see with the data if it could be 0 given its standard error, right? So how do we do this? We get the test statistics. So this is the slope. This would be our 0.519. So we would do it like this, 0.519, right? And then we have the standard error of the model. We calculated that a few slides ago, so let's find it. Standard error of the model. That little SE right here. We want this one here. It was 4.36. So let's go back down. 4.36. Right? Because that we know the slope, we know that, and then we need the square root of the sum of the squares of the x's, which we did last week as well. So we need to go back to that slide 9. Might be easier for you if you have it all together, but slide 9 gives us the sum of the squares of the x's. We need it, and it came to 4480. So we have those numbers, we plug all those numbers in. Did I overshoot? There we are. 4480. So we're testing the slope. Remember, the slope is so important. We don't really care what the value of the intercept is. It's sort of, the slope is what is multiplied by x, our explanatory variable. And by running this test, we're going to know if the explanatory variable is significantly related to the response. So it's really good to know how to do this. So, and 0.519. 4.36 divided by the square root of 4480. Keep all that in the denominator. Does anyone have a test statistic?
$7.967.
I get the same thing. Yeah. 7.967. Right. And so we want to get, what would you do next? We would want to get, we need to make a decision. So we can go, well, let's get our critical value T star. We know how to do so well. And yeah, let's use our alpha equals 5%. And what is our degrees of freedom for this test? 3. Who said that? Yes, it's 3. Good. It's always n minus 2. So it's n minus 2, which is going to be 5 minus 2, which is 3. Just remember, degrees of freedom for regression is n minus 2. And so let's look up that t value. So 3 degrees of freedom. Here we are here. 3 degrees of freedom. 3.182. Right. Two-sided test. It's a two-sided test. So we just look at that column, 0.025. 3.182. So this is why we spent so much time on this stuff, because this is where we really need it. So our conclusion. We compare T, right? This is our test, right? That's our test statistics. The observed T, we compare it to our critical value T. And what do we want to do with that? So we're comparing 7.967 compared to 3.182.
We reject our null hypothesis.
We reject, yes. So since, and it's always good to put it in notation, since RT is greater than RT critical value, you could even put test here and critical. It's always good to formally show it in notation than just the numbers, because the numbers only work for this. They only work for this test. But if you say this, then that's the standard rule for any numbers that you would have. So since the test statistic here, 7.967 is greater than our critical value, we formally write it like that, then yeah, we reject. We reject. And so since we reject this, we're rejecting this, right? And that means that it's not equal, that 0 is not a potential value for the slope. And we then say that, therefore, we can jump and say this, time spent is significantly related to sales. That is the real conclusion here. Because if the slope has no chance of being 0, then you truly do have a relationship between this and a good model. You have a good model, and it means that it will be a good predictor. time spent will be a good predictor for sales. When we don't reject, so when I run these, this is what I do quite a bit. I'll run lots of regressions, and the first thing I do is look for the p-value. I want to see the p-value or the critical value, like I just want to know, is it in or out? Because if the slope is out, then we don't have a model in this case. And when we get on to the multiple regression, we're going to be looking at several slopes because we're going to have several potential predictor variables, right? And you want to look at all of them because some might be in, meaning they're good predictors, and some might be out. Okay. All right. We can also, instead of the hypothesis test, we could also do the confidence interval. So 0.519 plus or minus, our critical value was 3.182. We have all the numbers up here. And then we want multiply by 4.36, yeah. That's a 6, divided by the square root of 4480. Right there. So this here, let's calculate it. So 0.519 subtract 3.182 times 4.36 divided by the square root of 4480. And I get, does anyone have a lower bound? We want to get a lower bound and an upper bound. And we want to make sure that 0 is not in there. If 0 is not in the confidence interval, we have a good predictors again, right? So you can you don't have to do the hypothesis test and the confidence interval. You can just pick one because they should give the same result. But we're doing both so that we know how to do both. Anyone have a lower bound? So I got 0.312. We're rounding to 3. Yeah, it's always good to round to 3. Even my standard error of the estimate, I guess we could have gone to 3 because it's going into more. It's always good to round to 3. It keeps our rounding error rate down. And we had an upper value. 519 plus 3.182 times 4.36 divided by square root 4480. Anybody have an upper bound? I get 0.726. So since 0 is not in the interval, we say time spent is related to sales. Even though we're testing the coefficient, we can say that the time spent is related to sales because it's a multiplier of the time spent. So it's pretty cool when it's used in this context, right? Really puts a lot of, we can see how practical this is. These tests all of a sudden are not just testing whether 0's in, it actually tells us whether we have a good prediction model or not. Okay. This is good. This is what we hope to find. This is really good. This is what we like to see. You go, yay. We have significance with our predictor variables. We have good data. Or what we're hoping to get. Okay, we can also calculate the confidence intervals and prediction intervals. So there's two types of confident intervals here. We have confident intervals and prediction intervals, and this is for a new, if we were to check for a new observation. So the confidence interval is for a new value. It gives us the average. And the prediction interval gives us an interval for the individual observation. Individual. See if that works. Okay, I think I know what it happens. I accidentally put on my my speaker on the Zoom call, and that's what happens. I just have to make sure I don't accidentally touch that. I didn't know what it was last time. Remember last week it was going. Yeah, was it last week or the week before, something like that? Okay. Confidence intervals. Okay, so confidence interval, prediction intervals, and so they have these big values, but we have everything, right? We know T. We know the critical value T, right? These are the critical values, T star. You can even put those stars because that's what they are from the table. The SE, we know those. We know N is 5. We know the this is like on a new X. A new X that we predict. And then we have the average X, square it and divide by the sum of the squares of the X's. So you can see there's only one difference between the confidence interval and the prediction interval. Do you see the difference? They're almost identical. You see there's one little difference between those two equations. Can you see the difference? There's only one difference between the two. Yeah.
Plus one.
Yeah, right here. And so there's a little bit more uncertainty when it's for individuals. So that expands the standard error a little bit more. So the margin of error will increase there because there's more uncertainty for an individual prediction than for the average. And I'll show you what that looks like in a picture as well. So here's what that looks like. Here are 5 points actually from the software. So you have sales, and then time in minutes, the time spent. Those are our 5 customers, 1, 2, 3, 4, 5. And the blue line is our regression. What was it? 75.222 plus 0.519x. That's the blue line. It's the least squares regression. The green are the confidence intervals. So if I got a new X, I could compute a confidence interval. There's just many point-wise confidence intervals going across all the X values. So we could compute one of them. We could maybe choose X equals 80 and we could get that confidence interval from here to here to here. And it would give us this. Okay, so that's the green. And then the prediction intervals are more uncertain. They're further away even more because they're based on an individual, not on an average. Okay, so you can see the difference there. There's less certainty for the confidence interval that's based on an average prediction. And then if you wanted to take a prediction for an individual point, like one individual point, then there's more uncertainty. Okay, so we have all that we need to calculate these. We could easily get these.
Can I ask a quick question?
Sure.
What's the difference between these confidence intervals and the one we just calculated with B1 plus or minus T?
Yeah, okay, so this one here, that confidence interval was for the slope. For the true slope. It's a good question because. It's a confidence, and it was a 95, we did a 95, right? So it's a 95% confidence interval for the true slope, beta. That's, because somewhere in the universe, there is a true slope and a true intercept. So we're testing to see, because remember, our slope value 0.519, that's just an estimate based on a sample. I could go out and get another sample and get another number. So somewhere out in the universe, there's a true slope for the true time spent, right, for that coefficient. And so that is the confidence interval for the slope, right? We could then do these confidence intervals. This is a confidence interval. Both of them are confidence intervals for the response. For the Y response. The true response. Because everything, if you think about it, the regression line is even an estimate. Right? These are all estimates, and anything that is a subset of the true full population is always going to be off a little. So it's going to be, we know there's some error, so that's why we do the confidence intervals plus or minus 2, right? Right. So if I was to get a confidence interval, let's say, on everybody's height, I would say it's, 163 centimeters plus or minus 5 centimeters. Right, so that's a confidence interval on the height. So we just don't have certainty when it comes to a subset. Like this is just 5 individuals. Does that? Oh. So yeah, so these are for Y. And so this picture is showing a lot of confidence intervals for the Y. Going right across for all different values of X. Okay. So if we're good. Let's try to do this. So we could do, let's do, I think I said 80, but why don't we try a new X for 90? So we could do for 90. So what we would do is for X equals 90, we would get Y hat equals 75.222 plus 0.519 times 90. And what do we get for that value? So 75.222 plus 0.519 times 90 is going to give me $121.93. Right? And so that is going to be a sales prediction, but I know there's some error with it. Right, like I know it's a prediction on the line, but I know that there's going to be some plus or minus. So if I was to look at this, I'm picking 90. 90 would be in between 80 and 100, so it would be about here. I'm plugging in this value and I'm going to get this, and we're going to build the confidence interval for plus or minus to the green and also plus or minus to the orange. I guess it's orange, is it? Orangey yellow. Okay, so that's sort of quantifying what the uncertainty is for $121. So this would be equal to 121.93 plus or minus, and it's going to be the same critical value. It's always n minus 2, so it should have a critical value of 3.182, because that's the critical value for the whole model. We use it for the slope and right. It's always on n minus 2 degrees of freedom. And then we know our SE, which is the standard error of the model. What did we use for that? Was it 0.36? And then we got to get this 1/5 plus 90 subtract the average, which was 62 minutes, divide by the 4480. there's our confidence interval. We can just keep boiling it down. We've plugged everything in, and remember to always state what formula you're using, because then it, you know, shows, it demonstrates that you know which method to use. And so you would write out that in notation and then plug in your values. Right? So let's boil this down. I'm gonna see if I can boil it down to a lower and an upper right out of the gates, just for space here. So 121.93. Subtract 3.182. Hopefully I can get all this in. 4.36 times the square root of 1/5 plus 90. Oh, let's get a couple of those. 90 subtract 62 squared. Divide by 4480, close the bracket and close another bracket. Whoa, I think I've got a lower bound. I put all that in the calculator at once to get a lower bound. I get $113. You're in that ballpark, that's good. So it's roughly $113. And let's say 34 cents. Two, let's get the upper bound now. See if I can get it all in the calculator at once. 121.93 plus 3.182 times the square root 1/5 plus 90 subtract 62 minutes squared, divide by 4480. I get, does anyone have an upper bound? Just let everybody catch up for a minute. $130.43. So what that means for this confidence interval, we're doing a confidence interval on the true prediction, really. The true predicted y. On the true predicted. Really the predicted y or response, but it's based it's the confidence interval on the prediction. So the line says that if you spend 90 minutes, the customer is probably going to spend $122.93. But you can also quantify it with, well, it's going to probably, I mean, that you really think the customer is going to spend exactly $121.93. No, but you can estimate that the customer will spend between $113.34 to roughly $130.43. $130.43. So that makes roughly between $113 and $130, instead of saying absolutely they will spend 121, because that's pretty precise, right? So we know there's some uncertainty to that, but we can quantify roughly a range. Okay, so that's on average. That's an average. For an individual specific customer, they come in, you would still get this value here. The only thing that changes is that one, because there's more uncertainty for an individual. So a specific customer coming in, this would be if you had a group of different customers, and on average, they're going to spend 113 to 130. Like that's based on groups of customers, but a specific customer would be a little bit more uncertain. So let's do that. 121.93. You're going to have the same values here. They're going to be exactly the same. Except for you're gonna have one more uncertainty in the denominator. Or in the radicand. There. We're gonna try this again. We got a minimum. Does that make sense? The difference, one's for like on average, and the other one is for one customer, an individual customer, not on average, or multiple customers. Okay. So this is the confidence interval. And this one here is the prediction interval. Both for a predicted Y. So here we go. So 121.93 subtract 3.182 times 4.36 times that. And don't forget to put the 1 in the, gotta be careful here, 1. See if you're able to put that all into one swoop. It really significantly reduces your rounding error because you're putting it in as one entire piece. And I did so, and I got a lower bound of $105.66 to upper bound. Now we can do the upper 121.93. This time we're going to add 3.182 times 4.36 times square root 1 plus 1 divided by 5. Lots of brackets in there will help. And I get an upper value of 140. Wow. I don't know if I did that right. I get 145. Does anyone get lower? Yeah, you get about the same. Okay, I think that's too high. I'm gonna do that one more time here. 121.93 plus 3.182 times 4.36 times square root 1 plus 1/5 plus 90 subtract 62 squared divided by 4480. Close the bracket, 130, there we go. It's 100, I get the same as what I got in my lecture. That's 138 point. I guess that would all round up to 20. Okay, so for an individual, we get, instead of a confidence interval, it's a prediction interval. So it's a prediction interval between $105 and $138. Those are our, this would be our confidence interval for the average predicted value. For a new X, let's say 90, we use 90. And this is the prediction interval for the response, for the predicted Y, using a new X equals 90 for an individual. And that's what we just calculated right here. These values right here on this. We calculated this value here and here. And then we did the second interval. It was even wider. You can see those are roughly going from there, those values. Right? So yeah, confidence intervals for the predicted values, right? The Y, and confidence intervals for the slope. Subscript stands for error. So it was like this. Standard error of the model was like that, right? Little subscript B for error. And then there is also the residual analysis. And we just, most of the time, we just look at these residual plots. And this plot here on the left is our least squares regression line. Right, this is our y. This is our y hat, which we said was 75. Right? And then if you imagine, so I tried to do this in the software so that that blue line becomes horizontal on the plot on the right. So just imagine the line going from like this to straightening out in a horizontal line and centering at 0. And so on the y-axis, you have y minus y hat. That's what all these values are. Like that's what those are. Right? So some y minus y hat are negative and some are positive. So if you look at this one here, this would be positive. This one ended up being negative. This was negative, and that corresponds to this one. So if you look at this is 0.1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5. Those are our 5 customers. So the plot on the right is the residual plot. This is the residual. U plot. So it's the residual plot. And again, you just take your y hat regression and just center it, just pretend you're just making it so it's completely horizontal and centering at 0. And then you have your points. You can see that the sum of all those residuals is equal to 0. The average of the residuals is also equal to 0. The sum and the average, because you divide by any number, it's still going to be 0. And this, what we want to see in a residual plot is lots of scatter. You don't want to have a trend at all. You want it to be, we call it structureless. And that's a good residual plot. And so this is nice. This is scatter. We have 2 above and 3 below. And I mean, we only have 5 points, but I'll show you some plots where we have more than 5 points. And so scatter, structureless, no trend, no pattern, that is a good residual plot. That's what we're hoping to see. Okay, so let's take a look at some of these. And it's against the minutes. So this is against the X, right? So this was Y against versus X, and this is Y minus Y hat versus X. So just to let you know, the plot on the left is just Y versus X. That's our scatter plot and our line. And then the plot on the right is the residual plot, which is Y minus Y hat versus X. Okay. And then you just look at these. So patterns in residual plots can take on many forms. We don't want a pattern though. We want to see no structure at all. And we want it to show across. So I'm just going to show you some of these plots across here. This plot here, that is not good. That means that, and sometimes this happens. We plot the data and then we look at the residual plots and it can reveal nonlinear relationship. And you might not see it in the regular original plot. So especially when you get into multi-dimensional data, you don't notice that. So you look at this plot and you go, we don't have linear data. So this is not good. I'll just put 2. I won't put X because that doesn't make sense. We'll put not good. This is not good. This is not good. We have a tunnel. A funnel. So can you see what's wrong with that? Like in terms of the model. Remember, we're trying to see, do we have a good model? So A, we start off good, right? Like the predictions look okay. And then, well, we start off actually more variability and then less variability. So the variance isn't constant. It needs to have constant variability right straight across. And here it's the opposite. This means the error is growing. Those errors are getting larger and larger and larger as you get to high values of X, which is not good either. This is not good either because this is not good because the bottom half, the low values of X are gonna maybe be over predicted, and then the high values of X are gonna be under predicted. So that shows that none of these on this page are good. If I had a residual and a plot that looked like any of these, I would not keep because the model would not be trusted. It's not linear. You have not constant variance. You have variance that errors that's growing. You have positive and then negative. It should be a mix of positive and negative right across from the beginning to the end. So this is good. This is what you want to see right here. No pattern. You have some above, some below, and that means that the fit is good. All right, so we're going to run a regression on set one. Let's go ahead and do that. Here is the raw data. And you can go, well, what is our n? N equals here. What would our n be? You're given, I give you these some x's and I give you some y's. And it's from set one of n's poem. What would you say is n? Just back it up so we can see. What's n?
11.
11, yes. N is equal to 11. We have 11 pairs. And then you can confirm 11 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They're all there. Oof, they made it. Okay, so what we're going to do is get the average for the X bar and the average for the Y's. And we can calculate those. You just simply add them up, right? You can get the sum. So the sum is just going to be like that. So the sum of all those is 99, I believe it is. Divide by 5. Just going to move this one over. Just see if you get the sum. I get 10 plus 8 plus 13 plus 9 plus 11 plus 14. I believe it's 99. Or is it 9.9? I don't think it's 99. What is the sum? 10 plus 8. Yeah, 99. So the sum is 99. Okay, 99 divided by 5 is 19.8.
So why did we divide by 5?
Oh, we want to divide by, yeah, I'm still thinking of the old example. Thank you. I'm thinking, why is this so wrong? It's divide by what? 11. Good. And we get our number that matches my lecture notes, 9. Okay. And we want to do similar for y, which is the sum of the y's over n. I was still stuck at the online tab feature. Sum of the y's, I get 82.51. Let's verify that too. Two 6 plus 10. I got 82.51 exactly. And we want to divide by 11. Oh, that's good. Divide by 11. And I get 77.5. We'll just keep it to that. It would be 7.501 if we wanted to be really particular, but let's keep it like 7.5. It's fine. All right. what are the sums of squares? So now we're gonna get those sums of squares. So let's grab the formulas. And we'll do, who shall we do first? How about the x's first? That's going to be this formula here. Remember our n. So the sum of the x's squared, that is when you need to take each x and square it. So you need to do it like this. It needs, so here's our x's. We're going to take 10 squared plus 8 squared plus 12 squared, and you just keep going until you get a value. I hope you got that. And we already calculated the sum was 99. And we said divide by not 5 by 11. See if you get that. So what do you get for your sums of squares? You haven't, just feel free to jump in if there's any corrections made. Thanks for the corrections, let me know. I think we're good so far. Yes. 1001. 1001 is what I get when I take each x, so 10 squared plus 8 squared plus 13 squared, 11 squared, 14 squared, plus 6 squared, plus 4 squared, plus 12 squared, plus 7 squared, plus 5 squared. 1001. And then we already did the 99. And then we know n is 11. And so altogether, I get 110. Right? Next one, we can get the y's. Do the same thing. It's the same formula, but with y. And let's calculate what we got. And we already calculated 82.51. We know that's good. We want to square that and divide by 11. We believe that should give us 41.273. I believe. I try not to make the mechanical errors, but it can happen. That's why it's so important to write down the formula. Right, because it keeps everything straight too. It reminds us of what we're doing as well. So then finally, the last one, sum of the squares of the pairs is we multiply each xy pair and then subtract the sum of the x's, which we have, and the sum of the y's and divide by n again. So if you go through each one and multiply them, I get 797.6. And then we get 99 for the x's, 52 or 82.51 divide by, of course, our 11. Really important we know these three quantities. We can verify that, right? 10 times 8.04 plus And then you would do the next one, 8 times 6.95 plus 13 times 7.58 plus 9 times 8.81 plus 11 times 8.33 plus 14 times 9.96 plus 6 times 7.24 plus 4 times 4.26 plus 12 times 10.84 plus 7 times 4.82 plus 5 times 5.68. Is it 794? I get 794.2. Did you guys get that? For this value here? Does anybody else get a different number? I'm just doing a QA. We always do a QA, right? Quality assurance. Anybody get anything? You got that? Okay, I might have done a different number. So no, we're in agreement with that. So if we calculate that, I get, and see if you do too, 55.01. All right. Good. We're good. We can then go on to the next question. So those are the three sums of squares. This is the kind of things you'll be doing in the lab on Wednesday. Right. And so just to back up, we're doing Anscombe quartet set number 1. And all of these, by the way, all of these data sets, there's 4 data sets, and all 4 of them have the same means for the x's, the same means for the y's, the same standard deviations for the x's, the same standard deviations for the y's, and the same correlation, which is incredible. No, he never revealed how he did it. He just worked through the numbers. And so because of that, they all have the exact same regression line, but they look completely different. So pretty amazing when you think about how. Right, so they all have the same summary statistics, but visually completely different look, right? So the first, or the next question is, what is the slope coefficient? That's gonna be, let me just change color, I'll go back to my purple. That's gonna be, B1 is equal to, and definitely use your formula, right? You get half your marks almost for doing this. It's just that, knowing this tells yourself even that what formula it is, because it's always a good habit to write down the formula, because getting straight to the numbers, you can see mechanical error can occur. So 55.01 over 110. Right, you just take 5501 and divide it by 110 from here. And we should get, which is half, right? It's just a half. So we will do that, 0.5. Right? What is the intercept? So we can then do that, that's B naught times the average of the y's, subtract B1 and multiply it by the average of the x's. So the average of the y's came out to be 7.5, I believe. And then we subtract 0.5 and multiply it by the average x, which we said was just 9. Just gonna make sure, 7.5 and 9. And we get 3. Is it just a 3 by itself? 7.5, subtract 0.5 times 9, yep, 3. All right, so we can put all that together. But what is the correlation coefficient? So we want to know what the correlation is. Now remember, all four sets had the same regression equation and the same correlation. So if we're calculating this, we can do this formula right here. Numerator is xy, sums of squares. Denominator is the sum of the squares for the x's, multiplied by the sum of the squares for the y's. So 55.01 in the numerator, square root of 110, multiplied by, and we got 41.7273. Does that look good? Yep, I see agreement. It's always good. So let's try that. 55.01 divided by square root 110 times 41.273. 0.8164. 0.8164. And then the next question is, what is the regression equation? That's just going to be y hat equals, our intercept was 3. You can always put this too. It's nice. It is good habit to do this too. Right? Which then you can just write it. I like to see the whole thing like this. What was it? Plus 0.5. It's always good. Just state what the regression line is. Doesn't hurt. Know that you have an intercept and you're adding a slope times the x. And that is our regression equation right here. As trivial as that may sound, it's good. We are pretty precise when we do formal reports in industry or academia. You still want to show your equations. So that line, believe it or not, the 0.8164, all of these sets right here have a correlation of approximately 0.81. Isn't that amazing? And the same means and the standard deviations. Okay, so we're going to make a prediction here. Let's make a prediction. Using that regression line for Enscombe set 1, what is the predicted value y hat for x equals 8.5? So we can do this one together, and then I have a set of clicker questions again to do. So what would we predict? What would you give for an answer? We'll do this one together and then we'll get the software and go through some questions. So first thing first, write out what your equation is. There's your equation. And then you want to go for x equals 0.8.5. That's going to give and just sub it in, substitute that in, and we get an outcome. We would also, before we get doing predictions, we would want to assess this line. We would want to go, okay, is the slope coefficient significant? i.e. is, x significantly related to y. We would also probably want to get the r squared. We would want to look at the residual plots. You want to do that whole process, get the standard error of the estimate, right? You would go through the whole process before you jump to a predict. I'm kind of jumping ahead to the prediction. So 3 plus 0.5 times 8.5, what do you get? I get none of these. You get any of these? I don't know where these came from. But if you had to pick, we probably have a bit of rounding, but I think that probably should be 5, right? Yeah. So it ends up being 7.5, I believe.
I got 7.25.
Okay, 3 plus 0.5 times. 7.25. Oh, okay, so it would round to that, right? Right? Yeah. So yeah, that would be okay. All right. It would round to 7.3. Okay. And what else do we have? Another prediction. Let's try it again. Another prediction. Y hat equals, we're still with the same Anscombe. So we're going to sub in x equals 12.5. You can have your arrow. So the lab on Wednesday, you're going to be working with your own data that, of course, it was anonymous. We don't know individuals, but we're using some of the data from the Qualtrics survey that you filled in at the first lecture. So you're running regressions on that data. It worked. And you can analyze whether you have significance or not with your data. Okay. Anybody get an answer? We have an answer. Yeah.
9.25, so C.
Yeah, it's gonna be just rounded again, right? Good. Right, so you can see this is one of the main reasons. So did do it, right? R was. Did we calculate R? Right here, 0.8164. So let's go down and do 0.81. And square that. What do we get? 64 equals. What do you guys get? 0.8164 squared. Shouldn't be too difficult, right? Yeah.
0.6665.
Yeah. 0.6665. Or we can say 66.65%, which in real data, that's very good. If it's real data, although this was Anscombe simulated, human simulated, right? Simulated data. So yeah, 66.65, which would be considered a good model. The standard error of the estimate. That's this value. E, the S for standard, subscript E for error. So the standard error of the model. You can say of the model. I'll just break down here. Standard error of the model. And that equals the SSE divided by n minus 2. Square root. So we don't have SSE, but we can find the SSE using, we have multiple ways to getting the SSE. We could get the SSE from this. Let's try it from this way. And do this. This is a different way, squared, divided by the SSXX. It's one way to do it. If you do it in multiple different ways, you may see a little bit of rounding error, which is fine too. You will get that because the formulas might be off a tiny bit. With the formulas are good, it's just the numbers might be off a little bit. So I get 13.763. Two, 7, 3. Yep. Want to verify that? We're good. So that would be 41.273 subtract bracket 55.1 squared divided by 110. Need to put brackets there to get it, to make sure it stays, to if you need to with your calculator. I get 13 point. I got a different number. You got a different number? 13 point. Yeah, 673. So I'm not sure why my notes are not right, but it's 673. Instead of 763. I've just written it backwards. Okay, so that we're not there, we're not finished, we have to put that into here. So 13.673 divide by, what was our n again? 7, right? So we will go 11 minus 2, that'll be 9. That's gonna be 13.673 divided by 9. And that should give us our standard error of the model. That should all boil down into 0.673 divided by 9. What I get one. Anybody want to tell me what they got? Go for it. Drum roll. We can take an average. No, we will be precise. What do we get? I get 1.2, yeah, 3. Anybody get anything different? It's good. All right. All right, good. And that's nice and small number. It's a small number, right? 68% of the errors would be plus or minus 1.233. 95% of the errors would be 2 times 1.233, right? Plus or minus within that. And then you can also run the hypothesis test. So what would be the null and alternative? What is the standard null and alternative for the slope? So we're doing the slope. So we would say beta 1, because that's the true slope. Remember, B1 is the estimate. Beta 1 is the true slope. And that's the estimate. Okay, so that's the difference. Versus, and we always just want to see, could it be 0 or not 0? Software programs, that's what they use. Equal to 0 versus not equal to 0. Because we test and then know if it's significant, right? So what is the value of the test statistic? You can just do a subscript test. And that's going to be our slope value, which was 0.5, right? And then we had our 1.233. If you want, let's put this so that you can see what I'm doing here. So I'm putting in B1 divided by SE divided by the square root of SSXX. These are new to you. It's always here. I've been saying all along, write down the formula, write down the formula. So make sure I do what I say. Right, so that's the formula. And then we can just plug in those values. Writing down the formula really helps keep this all completely straight too. 1.233, and the square, those sums of squares for the x's was just 110. So we'll get our test statistic and get the table value, the critical value. And then you know right away if you have a good model, this is a way to know if X is significantly related, if it's a good predictor. And Anybody at the back have a test statistic value? We're trying to get T. You wanna get your calculators warmed up for the clickers anyway, so. Anybody have a T? Pass. Go for it.
4.253.
Excellent. That's what I get to, 253. Thank you. You guys concur. Good. Agree, good, excellent, okay. Now we just need to get the critical value. We can get the range of the p-value, but we'll do the critical value too. Let's see, so this is gonna be, we're gonna use alpha, 5% or 0.05. And we're gonna get that critical value. So how many degrees of freedom does this test have? What would be the degrees of freedom? Pardon? 10? 10 degrees? There was 11 points, right? Everyone agree? Yeah,
9.
it's 9. So the degrees of freedom is in this for simple linear regression. Yeah. So we had 11 points, so that's going to be equal to 9. 9 degrees of freedom. So let's grab that critical value from the table. This row right here. And it's 2.262. 2.262. And we'll take that over here. Yep. And we could also get the p-value. I mean, if we want to get the range of the p-value, you could just go 4 point, what was our value here? This was 2 point, let me see. It was 4.253. Right, that was our T, and you can just go along this row, like just see where that is along this row. And it's gonna be between these two. Okay. Is that correct? Right? So the p-value is going to be this subscript times 2 to this subscript times 2. So it's going to be 0.001 to 0.002. That's how we get the p-value. So the p-value range is I'm not giving myself enough room. Let me just make that in the middle here. 2 times 0.001. And there's the p-val. I'll just do that to give myself room. 2 times 0.005. So the p-val is going to, the range is between whatever those are. It's going to be I think it would be 0.2 times 0.005 is 0.01. Point 0.002 to 0.01. Okay. That's pretty small p-value. So the smaller the p-value, the more strength against the null hypothesis, right? So, and the critical value is right. So since the t test is greater than the t critical, what do? And I can put down and small p-value. We can also, right? The small p-value also gives it away. What do? We reject. And we reject, and this is good, right? We reject the null hypothesis, and therefore X is related to Y. X is significantly related, it's a good predictor, and that's how we know we have a significant predictor.